talked about USR decomposition for the group SL1 or SU1, and also we have discussed about pattern decomposition. This USR decomposition is unique, and this pattern decomposition is not unique. So the USR decomposition basically says that any x belongs to G can be uniquely written as k bar x exponential of hx into n bar x, where k bar x belongs to k, hx belongs to dl and hx belongs to n. So today we will develop geometry of hyperbolic base. So here is the definition. A real geometric matrix A belongs to M and R is said to be positively defined if inner product of AB with B is greater than 0 for all 0 multiples B belong to R. And this is the standard Euclidean unit product. Let Pn be the collection of all positive definite matrices in M and R. Okay. So let A belong to Pn. I define a new map from Rn cross Rn to R by this thing Q, comma V. This is whatever the symbol is. This is called AU, comma V, and this is the inner product in Rn. This is the usually Euclidean inner product. Check that this is also an inner product. Okay. So this is the thing. Remember, this is the symbol we are using for standard Euclidean inner product. So let a U subset of Rn be open and connected. So let Q U to En be an R. Therefore, for each x belongs to U, this Qx is a matrix. So it has some coordinate Qij, x. Okay. We say that U is a smooth map. Smooth map. If this is x going to Qij exists, or 1 less than equal to 8. So this is a definition. Now, but I will define something called Riemannian manifold. But I will not define Riemannian manifold in full generally. Okay, so let us definition. Yeah, it is open setting somewhere, Rn square. Yeah. But that other. So, the definition. Let you subset of Rn be open. And connect. A smooth map Q from mu to Pn is called a Riemannian structure. So on U and U, comma Q is order management. So as I said that there is a much more general definition of Riemannian manifold, but since I will deal with only upper half space and Euclidean unities, for that reason this definition is sufficient for my purpose. Okay. Now, since this Q is a positive definite matrix, one generally associate a symbol to Q by this thing. Something like Q I comma Jx dxi and some dx. So, and in the language of differential geometry, this symbol symmetric 0 to tensor, and this is, I will call this as Riemann element. Okay. This symbol actually, this symbol is a, okay, let us call this star. Is a symmetric 0 to tensor. Called as a element. Now I will use this acronym Rn for this Riemann element. And I will use this acronym SC for smooth chord. Okay. So now we will define something, and after that we will see the example. So let u comma q be a Riemann element. Remember this Rn stands for Riemann element. So let P belongs to U. Okay. This then this TPU, what is TPU? TPU is the tangent space at P. So TPU, you know that this is really Rn. Because U is an open connected subset of Rn, so therefore TPU Rn. Okay. Now this Riemann metric Q, okay, I am calling this also Riemann metric. So Riemann metric Q will induce a inner product of TPU. So that inner product is, I will denote by this inner product, and there will be subscript P. This will be mapping from TPU and this U comma P belongs to TPU, and this is nothing but Rn. I define this thing U comma P. But this is U so angle between and this is an inner product space. If you with respect to the inner product we can define this angle. So angle between is U and P. This is visible cos inverse UVP and not so let gamma from A goes in double AP to U be a smooth curve. Smooth curve. This is SC. I am writing this SC for smooth curve. So what is the meaning of this thing? This means that is gamma from open interval AB to U is smooth in the usual sense. And in the other end point, so all derivatives, okay, one-sided derivatives, all order derivatives, and one-sided AN. This is the symptomatic. And whenever I am talking this gamma prime wave, that means it is the right hand wave. A gamma prime wave is this. I am interpreting this gamma prime wave as this right hand wave. Okay. So now let gamma get a closed interval a between a smooth curve. So I define length of gamma. So if I length of gamma is integration over from A to B is gamma dot T or gamma T, and this norm actually measured in the tangent space T gamma T. Okay, so what is this? What is the meaning of this? This is really my gamma dot T gamma T square. It's nothing but 2 gamma T. Okay, apply the subject to gamma dot T. Z1 on Z2 comes from any U. I define this thing D Z1 comma Z2. This is taking over length of gamma, where gamma is a smooth curve. Gamma is a smooth curve joining Z1 and Z2. So that means, okay, it can be shown that it's not difficult to also solve. It can be shown that D is a distance function of U. And topology English from U when sets or D from D when sets the original topology. So D is a distance function on this. So let gamma 1 from gamma 2 be two smooth curves in U passing through B6. So that means, so that is gamma 1 T1 plus A equal to gamma 2. So this is my picture. This is my gamma 1, this is my gamma 2. And this goes in this direction. This is my. So angle between this gamma 1 and gamma 2 at P is the angle between gamma 1 prime T1. U1 to U2 is called an isometry. So if I is a diffeomorphism, so diffeomorphism means that phi is a smooth graph and 1 1 and 1 2. Then you really take this B IP. So that's like derivative of IP. So that is by definition it is a map of well. This is P1 EIP2. This is an isometry. This is an unitary map. So actually I am not really so actually in calculus of scenario you know that deep typing is a map from U1 is suppose U1 is subset of Haar, deep is also subset of Haar. Deep typing is a linear map from Haar and U1. It is basically that. So that what does it mean? The meaning of this thing is really QB in a product P. This is function in a D piping. So let I U1 Q1 so Q2 be an isometry. The first observation is observation 1 is if you look at normal P. Very deep IP. So second thing is let gamma from AB to T1 be a smooth curve, and then this phi composition, if you compose with phi, so phi composition gamma is a called AQ2. So that because of this property 1, it is very easy to see that length of phi composition gamma is equal to length of. So because phi is an isometry, you can take this as an exercise if you are not able to see this. Third thing is if distance between P and Q. At where P and Q is of P1. Same thing as distance between IP and phi. So phi is actual distance. Fourth thing is so let's okay so at gamma 1 gamma 2 be to smooth curve in U1. So angle NU1 or symmetric. This angle between this gamma 1 and gamma 2 are E. That is this is the same thing as uncalculated. I conclusion number one and I conclusion. So now we will discuss some examples. We will use this identification of C with R2. Okay. So this X plus IY will be identified. Okay, so this first example one is this is the geometry B. And what is Q here? Q of this J. That means Q of X comma Y. This is the same thing as Q of X comma Y. The J is equal to X plus Y. This is the open subset of R. So this is J1 1 by 1 minus Z square 0 square. So this is nothing but this matrix 1 by 1 minus Z square into I. So clearly Q is a, for each Z, QZ is a positive definite matrix because Isometries are positive and symmetric. So and Q is also smooth function. So what is the corresponding matrix? Metric is what will be this is dx tensor dx plus dy tensor dy by 1 minus x square minus y square. So in actually in differential geometry, we will use this. We write dx square as dx tensor dx. So that is same thing as dx square plus dy square. That is like dx square plus dy square plus 1 minus x square plus square. So this metric is called the point pair metric. This is called the and with this Riemannian structure on the D, this is called D is called point carriers. So example is that. So with this Riemannian structure, this is called point carriers. Now second example. Second example is your own architect, and that will be called point carrier comma. What is the metric here? Metric is U of J is there is dx square plus dy square by 4 y square. I am taking this for some reason. So this is the metric on this Oh, sorry. Qz should be so right. So Z is equal to 1 by 4 whole square. And this matrix is gx square dy square y. Now, the exercise. So then, this thing, Gaussian application from H to this thing, dx is I by 4 y square. By 1 minus square square. This is an isometry. So if all what was the calculus? Z is equal to z minus z. So this is a very easy exercise. I believe it. Definition. Let Q2, Q clearly imaginary. So I use this notation. This is not technical. This thing isometry is the collection of all map I am using so that I is so now onwards actually we will mostly concentrate on two Riemann manifolds, that is really upper half plane and basically since these are isometric, so it is sufficient to really concentrate on one particular Riemann. So now I want to give an definition. So and for us now, this is given is called tensor. And when I am talking about Riemann structure on this HRD, you should understand that I am talking about this point element. Because this and the upper half plane, this that matrix. So always you assume that these are equal to this point. So they call a smooth curve joining Z1 and Z2 is called a geodesic. So the joining is called a geodesic. Joining is Z1 and Z2. if length of gamma is equal to distance between Z1 and Z1. Actually, this definition is specific, only specific to this when there are one update and this will be this calculation will not work for generally. This is only specific to U equal to H or U. Observation. So let Z1, Z2 belongs to really let gamma be 1. So I think this is Z1. So gamma, then gamma is geodesic. Joining Z1 and Z2. If and only this length of gamma is less than equal to length of gamma 1 or n for joining any called gamma 1 joining system. So let gamma be a curve joining Z1 and Z2. This from this definition it will call from this star totally will call that gamma is a geodesic joining Z1 and Z2. If and only length of gamma is less than equal to length of gamma 1 or any curve gamma 1. That means this is called gamma is the shortest path between Z1 and Z2. So that precisely says that. We come back to this while cavity picture. So for that in Paladis picture, G is called as U. And we are in the base picture. So that LG T1 R from D to D given by this LG of grade is very G dot. So G where G belongs to that G belongs to this G. So that means this may not be mathematical speaking. And one thing exercise you can check that is LG belongs to the isometries. This is a simple exercise. Actually, I have done this exercise in my note. You can see can lead to it. So LG belongs to isomer. So therefore it will follow that the distance between Z1 and Z2 is really isometry of D. So this distance between Z1 and Z2 is really distance between G dot Z1 and G dot Z2. And second thing is if gamma is a geodesic, gamma is geodesic. If you apply this G dot gamma, that is also geodesic. Because these LGs are simply isometries. Now I want to pay little more attention. Is there any question? So far in the definition or something, some clarification. Gayatri, do you have any question? mixture of the event types. Now, this is my origin. Okay. So, what is the Riemann matrix here? Uz is really 1 by 1 minus z square okay, I. So if you look at this, what will be B there? If B belongs to this TZ. So that will be, if you plot the limitation, that will be what? This B. Okay, so that is 2Z B square root. And that will be what? It will be really B. This is now, so pick some zero that is equal to what? So this is my point 0. Now let gamma be the curve, gamma t is equal to t, and t less than equal to 0, t less than 0. So this is the curve basically, and gamma. So I want to show that this curve gamma basically geodesic. This is my curve gamma. So I want to show that this gamma is a geodesic joining 0 to 1. So for that part I need to show that I will take any curve gamma 1 joining this 0 data. If I can show that length of gamma is less than or equal to that in length of gamma 1, then I am done, right? So that is the basic definition of geodesics. So let gamma 1 be any gamma 1 from 0, 1, 2 be any smooth curve so that gamma 0 is equal to 0 and this gamma 1 good. Gamma 1 is equal to okay. So gamma 1 sorry. Now so this implies gamma 1 t is, I can write this is x1 t plus I of I1 t, okay, x t plus I of t. So t belongs to 1. So this is my picture. So 0, this is my 0, and this is my R. And this is my some gamma 1 is. Now I define a new curve, gamma to t. So just simply I will take this x2. Okay. I am using this gamma 1, I am defining gamma 2. This gamma x2 and the domain is 0 and what is gamma 2t? Gamma 2t is this basically. So gamma to T is a reparametrization of gamma. So observe gamma 2 is a reparametrization. Okay. So you know that length of curve doesn't really change with when you reparameterize thing. So length of gamma 2 equals thus length of gamma 2 is really length of. So now what is length of gamma? So what is length of gamma 1? The length of gamma 1 by definition is really 0 to 1. Gamma 1 dot c and gamma t. And if you use the definition of that thing, this is really 0 to 1. This is really x dot t square plus y dot t square. Y dot t square. So y dot t square by square root. This is 1 minus x t square minus y t square. Yeah. So you use that definition. So and this is big. There is certain limit greater than equal to 0 to 1 x dot t bar by 1 minus x t square minus y t square. Now this is certainly greater than equal to 0 to 1 x dot t or minus 1 minus h t square. And this is nothing but your length of gamma 2, right? By definition. And this length of gamma 2 is equal to length of gamma. So this is so this is the length of gamma. So what we are getting? So we are getting the so thus. So okay. So let me get this. So thus we are getting length of gamma is length of that length. Okay, where gamma 1 is any part joining 0 and 1. So this also says that this gamma is the unique geodesics, joining 0. Uniqueness is also important. So conclusion. Gamma is the unique geodesic joining 0 and 1. So now so that means it says that if this is the picture of my disk D. So this line actually is a geodesic. So this line is geodesic. Now let us calculate what is the distance and okay. So this is the geodesic. This is the geodesic. This is small. So what is gamma? The distance between 0 and gamma. This is the distance length of gamma. Gamma is this curve. Gamma t is equal to t and t in between 0 to 1. So if you plug in the definition, so this will be 1. This is 0 to r gamma prime t 1 minus gamma t square dt. This is again 0 to r 1 minus t square dt. And if you do simplification this will get half log 1%. So distance between 0 and some point r is really half logarithm of 1% by 1 minus r. This is it. So this thing is really 0 to this line is a geodesic, and this is the unique geodesic path. If you take any point R here, this is the unique geodesic passing through 0. Now you know that this L3 is belongs to isometry of P. So that means if gamma is a geodesic, G dot gamma is a geodesic. So if you will apply the element of K, so that will basically rotate this line. So that means every radius is a geodesic. So these are also geodesic. So conclusion. Each diameter calculus is 1, each diameter is geodesic. So second conclusion is what? If you take any z belongs to D, so what is? So for any z belongs to D, of course the radius which really contains z, that is a geodesic, but that is also a unique geodesic, because here actually you are getting unique. If here you get suppose 2 geodesic, and if you rotate that to this line, then you will get also here 2 geodesic, and that is not possible. Okay, so line is the diameter containing 0 and z is the unique geodesic. Passing through 0. Now let Z belongs to D. Then we know that there exists some K belongs to A. If so that K dot Z is mod, right? Then if you will rotate that, you will get to this mod Z. Okay, so then now what is this distance between 0 and J? The same thing as distance between K dot 0 to K dot 0. And this is nothing but distance between 0 and mod Z. And that is what? We know that distance between 0 and R is half log 1 plus R, right? So half log 1 plus R Z plus. Now, okay, so let us remove this. Now we want to really calculate the distance between any 2 points Z1 and Z2. So let Z1 comma Z2 come to. So let phi of Z is really Z minus Z1. I1 minus Z1 by Z. If you have incomplex analysis, when if you have calculated this automatism of this, then you must have seen this. So phi of okay. So let G is called 1 minus Z1. It's really minus of Z1 bar. So this is matrix I have done. Then I took this. And this matrix belongs to SU among 1. And observe G dot Z is really higher. So this, so G dot Z1 is really what? Higher Z1 and that is 0. And G dot let W is equal to G dot Z2 is equal to really higher. Now, what will be distance between Z1 and Z2? Distance between G dot Z1 and G dot Z2. And this is equal to distance to 0. And what is G of Z2? This is the very phi of Z2. So phi of and this is relative 0 and Z2 minus Z1 by Z2 minus 1 minus Z1 by this is really log. Okay, so you can calculate using this formula. Yeah. This is right. So using if you will use the you will get something like log 1 minus Z1 by Z2 plus Z2 minus Z1 minus Z1 by Z2 minus this is the distance between 2 points Z1 and Z2. So we have calculated it, but we want to understand is what is the geodesics between Z1 and Z2. Okay. So think we should be giving this thing. I think you remember this. Okay. Okay, so you know that this is my say Z1. This is my say Z1. Okay, and this is my say Z. So I am applying some element of G so that this G dot Z1 is 0. So this is 0. And I am applying this in the element G so that I am getting G dot Z2 is W. So G dot Z2 is say here is W. Now you know that there is a unique geodesic between passing to 0 and W. So this means that there will be a unique geodesic. There will exist a unique geodesic between 0 and W. And what is the geodesic 0 and joining 0 and W? Okay. So geodesic joining 0 and W is the diameter. Okay. And diameter means, and that is really perpendicular to the boundary. Okay. And since G is an obvious map, so and what will be the geodesic joining Z1 and Z2? That will be the image of this map under this map G inverse. So here what I am saying, the geodesic joining G1 and W is a diameter. So it will imply that the geodesic joining between Z1 and Z2 will be image of this map under this map G inverse, where G is that map. So since this Mobius map actually takes a circle and it preserves the angle, so geodesic joining Z1 and Z2 will be a circular arc perpendicular to the. Because the original geodesic was a circular arc which was perpendicular to boundary. For that reason, pull the boundary. Okay. So that means the picture will look like this. So if you include this diameter as a circle, if you consider this straight line as a circle, so all geodesic in D are really circular arcs perpendicular to boundary. And I am also including, as I said, that we also include diameter in this. So this is my picture where it is D. So what will the geodesic? This angle is 90. Okay, so this is a really geodesic. This is a geodesic. This is a geodesic. This is question to measure Have you seen this picture somewhere? Arki? Where? Niger. This is the this is the Niger logo. Okay, so we have really understood this. Now, another thing we will use the stage. So, this thing, this is this real axis. And I told you that in the previous lecture, any point here it can be written as 80.0. So, one thing I could have taken here, so I will write. So here actually between any two points Z1 and Z2 there will be a unique geodesic. It doesn't really, it is not true in generally manifold setup that between any two points there is a unique geodesic. Where it may have infinitely many geodesic between any two. But in this particular thing, upper half plane or this feature, between any two points there will always exist a single unique. So that remark I should make. Okay. And that unique geodesic is a circular perpendicular. Now the thing is, any point here, if is of this point 80.0. If so, now you can calculate the distance between 0 and 80.0. Okay. This is really actually okay, this is an exercise. Two lines. Okay. Now, okay. So now we want to really go to the upper half picture. Yeah. Then I am still in time. Okay. 10 minutes, right? I suppose I have to take this, right? Okay, so the thing is, that so this is the thing. Upper this to this upper, then there is a math, this is inverse of the challenge. And geodesic here is actually circular arcs perpendicular to gravity. So, and here also, what will be geodesic here? That will be also circular arc perpendicular to gravity. So, geodesic in H will be circular arc perpendicular to the boundary. So that means what will be the picture of geodesic here? This will be. So these are the circular arc perpendicular to the boundary. So these are geodesic. So this is logo for your NCMs. So this NCM. Okay, so this has connection to something called Euclid's fifth postulate. you can see that what is the length. Okay, so now, okay, so I can. You find something very common. We have something called G is equal to A. Now, rotation. This let's say this name. This stands for this is ZC. Z centralizer of A. And what is by definition? This is really what K collection of all K, so that K is equal to say K for all K not K. And this is an exercise to check. This two-line exercise, the two K line exercise name is to be cross minus and I have also done this exercise in my note. You can see that. See in my note. Now just I will define something called. Okay, so G has many decomposition. So G has can be written as A or this NA and this K and this K plus further K. So now consider this 5 decompositions. Suppose K. That means if any G belongs to G, it can be written as something like K. Now this group K is isomorphic to this group 0 to 2 pi. Modulo, and this is nothing but S1. So this group has a measure set dk. And what is dk? So dk is nothing but d theta by 2 pi. This is a measure on this group A. Similarly, this A is isomorphic to R. Therefore, you can compute this A with a measure dA, and dA is nothing but the usual level measure dt. Okay. But dk is the measure and dA is the measure on A. And this thing. I'll just N is the isomorphic to the it has measure D and DS. This gives the level measure. So I can take this define some new measure. So G is equal to K. So I define a measure G is equal to the power log A. Log A D K D A. This is a measure on G, and this is K coordinate. And this measure is really left independent, right independent. What is that mean? So DZ is a so 1 is KA. So DZ is a left and right indirect measure. So what does that mean? That means this means if you take this thing f of x a integration over g e to the power 2 log a dk dA dA. This is same thing as integration over f of k and this thing. I will just write this line and I will come. This is control. Okay, so what I am saying f of x k a n to the power to log n dk dA dv integration over g is really f of k a n into the power to log n ck dA of k a n x. So this measure is left indirect, right Harmonic indirect measure, and this type of measure is called Haar measure, which you will study in detail. And this measure is unique of the scalar model, positive scalar model. So this is the thing. So tomorrow actually, tomorrow is my last class.